Good morning from Sweden and good afternoon in India. Today we have two lectures on heat transfer, two different aspects of heat transfer. One is heat transfer to surfaces in the fluidized bed, and the other is heat transfer to particles in the fluidized bed. So let's start with this first lecture on heat transfer between bed and a heat transfer surface in the bed. This presentation starts first with bubbling beds and then goes into the circulating beds. Traditionally, heat transfer was very much studied in bubbling beds to heat transfer to tubes in the bed, because it was initially when the fluidized bed combustion was started, it was thought that bubbling beds were the actual beds to be used, and to cool the bed, heat transfer tubes were necessary in the bed. But after some time in the 1980s, it was discovered that these tubes could not be kept in the bed because of erosion. So there was a transition then into circulating fluidized beds. But the heat transfer in bubbling beds is important because of fundamental reasons, traditional reasons, and also because of the external heat exchangers that are used in circulating fluidized beds. But then lower fluidization velocities are used in order to reduce erosion on the tubes. Okay, let's start with the definition of heat transfer, which is this equation 1. This is the heat transferred is related to a heat transfer coefficient and the surface and the difference in temperature between the surface TW and the bed TB. All of these, it seems very simple, but one has to be careful. So the heat transfer coefficient is that from the bed to the surface of a tube. But then you have to calculate also the heat transfer through the wall of the tube and to the medium that flows inside the tube. So what I'm dealing with is only the external heat transfer to the surface of the tube. I will discuss later the surface, what is that? And TB and TW also have to be stated carefully. So let's continue. First of all, the heat transfer coefficient for simplicity is assumed to consist of a radiation term H sub R, and the gas convective term and the particle convective term. And these are assumed to be additive. Fundamentally, maybe they are not completely additive, but this is an acceptable simplification. And also, sometimes the gas convective and the particle convective heat transfer terms are added together, so they are added. The surface is not so simple because, as I have explained previously, the walls of a combustion chamber usually consists of membrane tubes. That means tubes with steam or water inside, and then these tubes are connected by fins to form a surrounding membrane surrounding the furnace. So the surface could be either the projected surface or the total surface, and there is a difference, a coefficient between them. Of course, projected surface is some kind of straight surface like this, whereas real surface takes care of the curvature of the wall. And it's easy to derive theoretically how to calculate this coefficient that changes between total surface and the projected surface. You have to be careful when you study heat transfer coefficients from the literature, because it's not obvious that it is related to one surface or the other. So one has to pay attention to this fact. The particle or the convective heat transfer surface is illustrated in this figure, where the heat transfer coefficient is here, and the logarithmic scale of fluidization velocity is found here. These curves are based on a model, so they are not really measurements, but it is a model. The model says that initially, when fluidization starts, heat transfer increases. Then it goes to a maximum, but then the bed becomes diluted, and finally the bed disappears, and then the heat transfer also disappears. So there is an important thing that there is a maximum heat transfer, and this maximum depends very much on particle size, as you can see here. Very fine particles have a very high heat transfer coefficient compared to the larger particles, like 0.5 millimeter particles and larger. This is particle convection heat transfer because of the movement of the particles. But then there is a gas convective also, which is follows this curve. The gas convective is because convection from the fluidization gas, but this fluidization gas is related to the particle size. So for small particles, this gas velocity is very low and its contribution is also small. Whereas for the higher particles, gas convection could become larger than the particle convection. This is another curve. This is a pressurized situation, but I have included it because it reveals that the curves may not be so, they certainly increase when at minimum fluidization velocity. They certainly go up to a maximum, but the decline is slower because this is a linear scale, and the previous figure was a logarithmic scale. This axis is a logarithmic scale, so it makes the curve look much more extreme than they are in the real case. So from the maximum and onwards, there is not constant, but not so much difference for long ranges of velocity. You can see another thing, that with increase in pressure, obviously, it increases. Now, most of the devices that we are dealing with are not pressurized, so we are only working at atmospheric pressure. The other thing that you can see here is it doesn't start abruptly at the minimum fluidization velocity, but there is a heat transfer also in the fixed bed, which precedes the fluidized bed at lower velocities. So in the fixed bed, there is also a certain heat transfer, but much less than in the fluidized bed. Some numbers I know from my previous experience that when I was a student, it was always difficult to remember the various dimensionless numbers. So I resume them rapidly here. This is the Archimedes number, which is related to the particle size, but it's a cube of the particle size, so it's very strongly related to particle size. We say that, well, Archimedes number is an expression related to particle size. The Prandtl number is contains physical properties of the medium, conductivity, viscosity, and specific heat. The Nusselt number is the heat transfer coefficient. This is the heat transfer coefficient related to the size, to some size. It's not particle necessarily, but it could be size of a tube in this case. And then the thermal conductivity of the surrounding gas. The Reynolds number is related to the velocity and some size, maybe size of particle, size of tube. but some characteristic size. We used to think of Reynolds number as a sign of velocity, fluidization velocity, for instance. So Nusselt number is related to heat transfer. And in fact, there are some relationship between Reynolds number and Archimedes number that I will explain later. But there is no velocity in Archimedes number, whereas there is a velocity in Reynolds number. So next figure will explain this better, I think. Yeah, you have seen this before. This is the particle Reynolds number, logarithmic scale. This is the Archimedes number, logarithmic scale. And you have previously seen the curve for minimum fluidization velocity and the curve for this terminal velocity of a single particle. But new here is this curve, which is the optimum velocity related to the maximum heat transfer. So it follows a situation where at very low Archimedes number, small particles is close to the terminal velocity, whereas at large particles, it is closer to the minimum fluidization velocity. And the other connecting expressions here reveals that there is a relationship between the Reynolds number and Archimedes number. And this is what motivates the interchange of Reynolds number and Archimedes number in some heat transfer correlations that you will see in the following. Here is an illustration of the various components, gas convection and particle convection. This curve is gas convection, and this curve is particle convection at the maximum heat transfer. And as I said before, gas convection is very small. It's a logarithmic scale here. Only at large particles, the gas convection becomes of same size and even larger than the particle convection. But the field of interest here in our cases is here, in this range of particle sizes. So in most cases, gas convection is not so important. This is an illustration of, I would like to say that most of the heat transfer correlations that you will see are taken for a tube in the fluidized region of a fluidized bed. But in heat exchangers, tubes are usually packed in some way in a linear arrangement or in a staggered arrangement. And then there is an influence between the tubes that is illustrated here. The numbers are not interesting because it is the kilocalories, but I want just to show the influence of the distance between the tubes here in the horizontal direction and between the various curves in the vertical direction. So in most investigations are made on single tubes, but then you have to translate this information by correlations just to take care of the packing of tubes in a heat exchanger. That's what I wanted to say here. I give an example. There are so many correlations on heat transfer. It was very much studied in the old time, and there are tens or maybe hundreds even of correlations, but they don't agree at all. And I've just taken one correlation, which is the one of Fredenberg here, which is considered to be the best one for heat transfer to a single tube, horizontal tube. But Fredenberg's correlation was later corrected by Andrén and Glicksman. So let's see what this picture shows. Correlations for various sizes of bed particles. And they are, of course, different because the size of the particles is so important. And then it is correlated with the fluidization velocity. And you see that Fredenberg's correlation just goes like this. And there is no maximum, it just goes on. Because at the time when he made his investigations, it was not clear that there was a maximum heat transfer. It was only realized later. So Andrén and Glicksman corrected this Fredenberg correlation and formed this correlation. And I saw a recent publication on heat transfer to external heat exchangers tubes, and they had found that this Andrén and Glicksman correlation worked very well compared to measurements. I don't give the correlation here, but you can, if you're interested, you can find it in the literature. There are other correlations, particularly the only ones that work well are those to maximum heat transfer. And an example is here, the heat transfer coefficient at maximum heat transfer is related to the particle size in Archimedes number like this. Very simple correlation. But this is particle convective heat transfer. And it was extended later by Baskakov. It uses a little refined expression, but the same for particle convection. This is gas convection. And he also added a Nusselt number for radiation. So this is the radiation heat transfer coefficient. This is the tube dimension, and this is the heat, gas conductivity. It is formulated just in the same way as the Nusselt number to fit into this equation. But the radiative heat transfer coefficient, I will show it later, is a little special. There are other correlations, such as very famous Zabrodsky's formula. It shows explicitly the importance on the particle size, bed particle size, gas conductivity, and the density of the particles. But it shows, I have expanded this into the parameters hidden here. And I find that this also shows a rather similar dependency on particle size, thermal conductivity, not exactly the same, particle density, and furthermore some properties of the gas. So they are rather similar. But the difference between this dimensionless formula and this is one problem with the dimensional formulas. You could ask yourself, what is the dimension of the particle size? If I have particle sizes of 1 millimeter, do I put 1 millimeter here? Or do I put 1 meter? Or which unit should I use in this correlation? It's not clear because all the units used are taken care of in this coefficient, and it's not explained. So this is why dimensionless expressions are better than the dimensional, although the Zabrodsky's formula is known to be one of the best. If you just know the dimensions, it's one of the best for the purpose. Okay, so this is the radiative term. It is, if you remember previous studies, radiation is dependent on the fourth power of temperature, the Kelvin in Kelvin, the Stefan Boltzmann coefficient, surface, of course, and now in this case, particular case in radiation, epsilon is, I have not changed it, it's emissivity. So otherwise it's usually in fluidization, it's voidage, but here it's emissivity. And this is the heat transfer between, heat transport between two parallel surfaces or two concentric tubes with these temperatures. And this can be written also with a definition of heat transfer, which is this equation, as I said before. And then these two together gives us the radiative heat transfer coefficient, which is now this one. It depends on temperature. It depends on the emissivities, on temperature, and if I make some coarse approximation, it is obvious related to temperature to the third power. Otherwise, heat transfer coefficients may not be related to temperature. Then the emissivities is the emissivity between the bed and between the wall that is receiving the heat. And this formula is also a classical formula in radiative heat transfer, so you can find it in any book. What is not found in any book is the bed emissivity, because the bed consists of particles and they have a particular particle emissivity. But because of the interaction between the particle in the bed emissivity is different from the particle emissivity in this way. Because of the scattering, the reflection between the particles, it becomes like this. I will come back to this formula and alternative formulas later. So the heat transfer is related to the bed temperature, and the bed temperature is essentially equal all over the bed. And essentially means that it's not completely equal, because we have some boundary layers with lower temperature, and there may be also some other variations in temperature. But David mentioned this thermal flywheel aspect of heat transfer. It is so much heat stored in the bed, so it is not so much disturbed by combustion and other disturbances. The only important disturbances are the boundary layer, thermal boundary layers that you have to be aware of. There is another thing that one has to be aware of also, and that is that heat transfer coefficients are derived for, as I said, rounded objects in a well-fluidized part in a bed. But here, the heat transfer coefficient has been measured along the wall of a bubbling fluidized bed combustor. The bed surface is here about 1 meter, and then this is goes to the nozzle bottom, which is here. And you can see that, okay, at the surface of the bed, we have a reasonably high, representative heat transfer coefficient, but then it falls. And the explanation is that in the bed, there are currents of particles developing. So the bubbles bring the particle up to the surface, and then the particle move down at certain places, and particularly at the wall. So here, the particle are moving down, and then, excuse me, and then they get cooled, and they are not agitated so much as they are in the bubbling, in the vicinity of bubbles. So the movement of the bed become damped here at the surface of the bed, and you see the heat transfer falls. So it is obvious that the heat transfer is related to the movements of the bed. You can see this in this picture taken at the same place as where the heat transfer measurements were made. And this measures the loss of wall thickness in millimeter during 1,200 hours. So you can see that a lot of the wall tubes have been eroded away, and particularly at the surface of the bed. And then they are less eroded towards the bottom, for the same reason as the heat transfer falls, because of the movement of the bed. The bed is less eroded here. And that leads us to the very famous model of bubbling heat transfer in bubbling beds, and that is called the packet model. And it's actually unsteady heat transfer of a packet of particles that is moved onto the heat transfer surface. It remains there for some time, and then it disappears. While it remains there, it loses its temperature to the wall. So it is a transient heat transfer to this packet, which is considered as some kind of unit. And it is modeled by the diffusion equation, as you saw yesterday, with the diffusion thermal diffusivity here, thermal conductivity here, and this is the transient term. and there is no gas convective term in this formulation. It's as simple as possible, because this formulation is so simple that it can be solved by conventional methods. These conventional methods is the series development, series expansion of the solution. And here is the first term of this. Series converges rapidly, so it is sufficient for the practical purposes just to take the first term. And this term is also averaged over the time of residence at the wall. So it is valid for a particular time of residence. It contains the heat transfer coefficient of the packet. Not easy to define, but this is what it is. And this is the density of the packet and the specific heat. And this is the time. This can be reformulated into a Nusselt number and another dimensionless number, which is called the Fourier number, which is the time, dimensionless time. It's just a reformulation of this equation. But those of you who are mathematically gifted realize that when the time goes to zero, a very short residence times at the wall, the heat transfer becomes infinite. And that is not physically reasonable. So it cannot be true. Therefore, it said that, well, the particles do not touch, they may touch the wall, but only in a singular point. And most of the space between the particle and the wall is a gas lens between the wall and the particle. So there is a gas gap, which is modeled in relation to the particle size here. And this is modeled as a resistance. So the total particle convection is this particle convective term and the gas gap, resistance in the gas gap. Here is the gas gap. You can see a packing of particles at the wall. And as I said, there are the lenses of gas here, and they may be thick. They may, even if the particles are not touching the wall, there will be some gas gap here. And this is supposed to have a certain thickness. So this is considered also to avoid infinite heat transfer coefficient. So actually, the heat transfer coefficient is this equation, which is, here you have the Nusselt number, logarithm of the Nusselt number, and the logarithm of the time. And this is the equation that I showed you. And then it is cut here by the gas gap. It is not defined, it could be different thicknesses of the gas gap somewhere here. And then at very long residence time, it goes in, it degenerates into thermal conductivity of a stagnant particle packing. So it is like a heat transfer in a packed bed. So the heat transfer coefficient moves between these two in the particle phase, but there are also bubbles. So at a certain part of the total time, the bed is covered by bubbles, and the rest of the time is covered by particles. So the particle part of the heat transfer is this one. This is what we defined previously. Then there is some gas convection which was neglected, but it is added here again. And then radiation, which has to be treated separately. In the bubble phase, you have some gas because of the movement of the gas in the bubble, heat transfer from convection, gas convection, and radiation in the bubbles. But usually these effects are very small. So in many practical situations, this equation is sufficient. Just the particle convective heat transfer, and then time of bubble time is subtracted. It's estimated and subtracted. You can have other formulations as well, but the essential thing is what I just derived. Then it can be modified according to the situation. So this was more or less a very short summary of heat transfer in the bubbling bed. And now we will take a step further and out into the circulating fluidless bed, which is much more difficult to study because of circulating fluidless beds usually are more extended and more difficult to assess, and the difference between laboratory devices and real devices are much more severe. Anyway, we start with this, which I saw recently in the literature. It shows that the temperature, the heat flux along the wall of a CFB boiler from 0, as you can see from the bottom to up to high altitude, is more or less constant. Here there's no heat flux because this part is refractory lined, so there is very small heat flux here through the refractory layer, and it only starts here, and there is a slight decline. This means load. This is 100% load, and then this is lower load. So at 100% load, we have a higher heat flux at the bottom than at the top. And it is not explained here why this is so, but I think basically it's because of a small change in temperature, not necessarily change in density, because of the contribution of radiation is so important, but the temperature, which also influences radiation, is declining a little, and then the heat transfer is declining. And that is probably the reason why at lower load, lower temperatures are present, and then the heat flux is less at lower loads. Yes, David was talking about the core and the wall layers. Particles were gathering at the walls and descending there. And here is the temperature aspect of the wall layer. The bed temperature is this 850 degrees, and the distance from the wall in a logarithmic scale is here. So here is the core of the bed, 850 degrees, but you can see that at various heights from the bottom, the temperature of the in the wall layer is decreasing because of the heat transfer to the cooled walls. And in fact, here you can see, I know the temperature of the wall. In this case, it was about 200 degrees. So and here we have this is 1 millimeter. No, this is 10 millimeters. So this is something like 6 millimeters, as close to the wall as one could measure reasonably well with the thermocouple. But then there's a jump from here down to 200. And I think this is the gas gap, because the heat transfer in gas is much less, and that gas film close to the wall is an insulation. So the jump in temperature is higher in the gas gap than in a particle suspension at the wall, in the wall layer. Yeah, this is another way of looking at it in a linear scale, and this is the wall temperature here, and this is the, close to the wall. Yeah. No. Anyway, this is the bed temperature in the core, and then this is the fall of temperature in the boundary layer, and then very close to the wall there is a steeper fall, but maybe not down here, but steeper like this. And the reason then is this gas gap that you between the particles in the wall layer and the wall. Gas gap of 1 millimeter or a few millimeters, so something like that. Okay. The wall layer as such can be illustrated in this figure, which shows square combustion chamber from above at a certain distance, 8 meters from the bottom. And you can see here distance from the front wall here. And this is a distance from the side wall up to the center line, which is this. This is the center line. Fuel is fed from this side, and the cyclone entrance is found on that side. So here you can see iso lines with flux, particle fluxes. You can see that there is an upward flux in the core, which is the circulation flux, but then there is a downward flux in the wall layers, and you can see particularly in the corners there is a very strong downward flux. In the wall layer in general there is a flux, but in the corners particularly there is a strong flux. So this is what we are talking about, the wall layer. We continue to make a measurement in the wall layer. This is time on the scale, temperature on this scale. We have 850 degrees again in the bed, but in this diagram shows the measurement of a special thermocouple setup consisting of 1, 2, 3, 4, 5, 6 thermocouples inserted simultaneously in the bed to different distances from the wall. And you can see that these thermocouples react, they increase and then they decrease. And it is rather simultaneous. So it's difficult to know what has happened, but I can interpret this as clusters of particles falling down along the wall. So they are they enter from the hot core, they go into the wall layer, they fall down there, and they get cooled down. Just like in the packet model, but here it is a much more dispersed situation. It's interesting to see that this thermocouple, which was 28 centimeters from the wall, measured a very smooth bed temperature. There were no particular thermal clusters there, but yes, in the wall layer, we had such behavior. You can illustrate this perhaps like this. This is the wall, this is the core, and this is the temperature from the core to the wall. This is the gas gap, and these are the clusters close to the wall, entering, leaving their heat, and dissipating, disappearing, or falling down further. This is probably the behavior in the circulating fluidless bed. We talk about the density of the bed. Density depends, of course, on the particle density. This is the amount of particles and their density of the particle themselves. This is the density of the gas and the voidage, the amount of gas. So of course this is very small compared to this. But anyway, this is the full definition, and it can be integrated over the cross section of the bed, and you get the cross section average density. And that cross-section average density can be compared with the pressure drop in the bed. This is pressure, and this is the vertical direction, and this is gravity. So the pressure drop, which can be measured, I think David showed some examples of pressure drop measurements in the bed. And this pressure curve in the bed the derivative of this curve gives you the density of the cross section in the cross section of the bed. So it is possible and not too difficult to measure this value. Because this is a very important then to use in correlations for heat transfer. Well, first the gas gap. The definition of the gas gap was a certain fraction of the diameter is the gas gap, and here we have the gas gap thickness, namely this delta, and we have the particle volume fractions from various experiments. Theoretically, you can derive a gas gap for as dense suspension, and from gas lenses, as I showed previously. Let me come back to this. This one, the gas lenses are shown there for a particular packing of particles. So this is theoretical, simply a measure, and it can be also defined for cubic arrangement of particles, and it looks like this. And then we have put it here a number of measurements. So some of these measurements are below what is theoretically possible. This is typical for many measurements, that you cannot trust them completely. There is always some difficulty, but the remaining measurements here are reasonable. You cannot trust them either, but they are at least consistent with the idea of the gas gap. Okay, so the total heat transfer coefficient, if the wall is covered by particles for a certain time and uncovered for the rest of the time, then here we have the covered time, particle convection, and the radiation from particles to the wall surface. This is the remaining part when it's not covered by particles. Then we have only radiation from some distance and gas convection. So this is one way to model the heat transfer coefficient in the circulating fluidized bed. And of course, the particle convective part is modeled like this, with this considering the gas gap at the wall. Yeah, the radiation is not easy, but on the other hand, radiation is very well known, and I cannot talk too much about the basics of radiation heat transfer. You can find it in any textbook. If you have two components, the particles and the gas, they can be expressed like their emissivity can be expressed like this. It's called the law of transmittivities, and it gives you a resulting emissivity depending on the gas emissivity and the particle emissivity, like this. And also the particle emissivity depends on the Brugère law of exponential decay in a gas or a particle, and it is this law which says that the particle cross section times the length of path length gives you a decay, or gives you an absorption which results in the emission of the particle suspension. Particle emission of the particle suspension is actually equal to the absorption of the particle suspension. And it all depends on the cross section of absorption. And the cross section of absorption, as you can imagine, it is the size of the particles, the cross section of the particles, times the number of the particles and the emissivity of the surface of the particles. So it can be calculated, because if you know the average composition, average density of the particles, you can, in a very accurate way, calculate the number of particles. And that is what goes in here, and then it goes in there, and you get the particle emissivity. The path length here is more difficult. One can imagine you can take a characteristic length of the case that you are studying, but in general it is used such a formula where it is related to the volume of the space divided by the surrounding surfaces of the space. This is just taken from some textbook. It is not necessarily correct. The correct thing you can find out by thinking yourself. Well, this is, I said before that this emissivity of the particles is not necessarily emissivity of the bed. And I pointed out there is a formula like this. It can be also derived in a more elegant way from scattering between the particles. And these two formulas, fortunately, give the same results. So it is rather well known. It can be used for calculations. Well, the heat transfer coefficient, as I have explained it earlier, is this one. And here there is an efficiency added. And the reason is that if we take the heat transfer coefficient of a bed, circulating bed, at the wall, you have a denser suspension than in the center. So and also the temperature is lower. So the wall layer may influence. But on the other hand, you need very refined calculations to treat this matter. If you just want to make estimations, you can use an efficiency. So this efficiency is one when the radiation can penetrate to the wall without any problem, and when the wall layer is almost absent, such as when the suspension density is low, then this efficiency is 1, because then the whole space takes part. But then when you have a thicker suspension density, the wall layer prevents the radiation because the wall layer is thick and it is colder than the core. So the radiation is lower, and it can be estimated. It has been done by some guy called Lechner and Baskakov here. So this is this, and then it is compared with various data from the literature. This data and this data and these agree reasonably well, if you may excuse. It is so rough that you can say that this agrees reasonably well, whereas this is obviously not correct. So you can also use this to analyze various data sets and see if they are consistent. We have used this to various data, and we have established then a heat transfer as a function of suspension density, the average suspension density over the cross section. And then we get a relationship looks like this heat transfer coefficient, logarithmic scale. And it is reasonable in the ends. It is reasonable for very low suspension densities where radiation is dominant with radiation efficiency 1. And then it is reasonable at the dense suspensions, but there we can subtract actually the heat transfer by particle convection, and then by means of this radiation efficiency, we can subtract what remains is the particle convection, and it is plotted here. And this is also reasonable. When the amount of particles is decreasing, then the heat transfer coefficient is also, from particles, of course, also decreasing. When it is a very thick suspension, then the particle convection plays a role. But it is a logarithmic scale, so you have to consider this carefully. On the other hand, it is rather rough. So bed temperature is supposed to be in the normal range, 800 to 900, and the tube temperature is supposed to be 200 to 300 or something like that degrees centigrade. So it is rough. It could be improved. Conclusion. I have shown a number of empirical relationships to estimate the heat transfer in bubbling beds. And I have said that the heat transfer to maximum heat transfer coefficients are quite good, whereas the other heat transfer coefficients covering the whole range of velocities is less reliable. But I have pointed out that there are some, Andrén and Glicksman and Fredenborg's correlations are reasonable for bubbling fluidized beds and for tubes in beds in a well-fluidized region of the bed, but not at the walls. And then I have indicated some modeling approaches, but these are mostly helpful to explain what happens. The packet idea and the density of the packets and the residence times and so on. It's just giving you a qualitative idea of what happens. It is difficult to use such correlations for very refined calculations. So the CFB was not so well described, but I have presented at least one correlation. But recently there are many new results published. I have seen recent 1 or 2 years from CFB measurements in CFB boilers. So a work should be done to compare these results and to compare them with previous results that I have shown here. So that is, I think, it from the heat transfer to walls.